So for this first tutorial, we'll be creating a simple camera classifier. And we'll demonstrate how with just a few lines, about a dozen lines of QML code, you can create a image classifier using a live camera. So to begin, we'll create a new empty Qt Quick application. We'll just use the defaults here and call this camera classifier. So now this creates a template application with just an empty window. So we can run it and see the canvas that we'll be working with. And there we go. Now we can import the Qt Multimedia package, which will allow us to open the camera interface. The first part is to declare a camera. You give it the ID simply of camera. Now, Qt Quick uses a video output widget, and this is what receives the camera frames. So as an ID, we can call it our display. Anchors.fill here will cause it to be to take up the full size of the window. And finally, we can set the source to camera. Now, if we launch this application, you will see me sitting in front of the camera. Hello. And now we're ready to move on. First thing, we should set the viewfinder resolution to VGA here. Okay. So now we're ready to import the DeepViewRT plugin. There we go. And this brings in a few different elements. So the first one, the basic element, is the model. And give it an ID of model, and this allows us to load our models. So we'll quickly go and create a model to work with over here. So to start, we'll just go download it right from TensorFlow's MobileNet models. So you can type in TensorFlow MobileNet 2. Here's the link. So we can pick any of these. Since we're just doing very simple processing here, we can grab one of the smaller models. So 0.5224 by 224. You can download this model. So in this package, there's a few files. We can import either the frozen PB file, protobuf file, or the TF-Lite file. So we'll go ahead and use the TF-Lite file for this demo. We've got a folder here with various models, but we'll add this new model to it. So the 0.5224, drop it over here, close like this, and open up the DeepViewRT model converter. So now we just give it MobileNet 0.5224. The converter supports TensorFlow Lite, TensorFlow, including the new 2.0 saved models, and NNEF, which is the neural network exchange format, which allows us to support all sorts of various file formats. A labels file. So these will, we kind of have to go digging for them sometimes, but this way when we classify a given output, instead of saying ID2, we can say what the object actually is. Typically, it's used alongside the model, but the RTM format allows these to be embedded directly into the model, which is a little bit more convenient to work with. So once we've loaded these, you just hit convert, and it'll take this TensorFlow Lite model and generate the RTM. It gives a report of the converter here. So TOCO means that it's taking the TensorFlow Lite model loader for the reading, and then does the conversion. As well as converting, we also apply the memory map optimization, which reduces the overall memory usage. So now we can see that the typical memory that would be required for this particular model would be about 24 megabytes, and we shrunk that down to 5 megabytes over here. So now we can close this. You can see in models that are 0.5 model is over here. I'm just going to copy the file name here so I don't have to type this all out. So back in our example source code, under model, we can now give file name. This is in home, pi models, and then the file name that I copied. So this will now load the model when the program launches. The next part is to attach the image classifier to our model. So the image classifier is the specialty wrapper around the model. So the model object is what allows you to load a model, and sort of it's what contains it in memory. From there, we have a few different runner classes. So image classifier is one. It'll take an image and give you a label associated with it. We also have an object detector, which again will take an image, and as its output, it'll give you a list of objects, their coordinates, and the label associated with them. So it's a specialization of how the model is run. The most basic is the model evaluator. So this is the bare bones wrapper around the model that simply runs the model. It doesn't do any sort of output processing, but you're able to read the output to do your own custom processing. So for example, the skeleton demo uses this to capture the output and do its own processing of the output to generate the skeleton coordinates on the screen. So we'll give this an ID of classifier. Model, points to model. So you could declare multiple models and have a classifier, a detector, all of these running in concert. They would all have their own names for mapping to each other. But in this simple example, it's the only model. The next little important detail is the normalization method. Now this can be encoded into the model at conversion time, so that it doesn't need to be set, it'll automatically do the processing. And why this is needed is models typically don't save the image pre-processing that's applied. So for this example, the mobile nets apply an image whitening or standardization to the input. At runtime, we need to match that same processing, and since it's not encoded into the model, we need to tell the classifier that this should be applied to the image input. So if we store it into the model at conversion time. It happens automatically. Otherwise, we can tell it which mode to use. And or finally, your actual model design can include the processing as one of the early layers before the model starts. And finally, to capture frames from the camera. So this is what we'll as the camera is playing, we'll capture the frames and feed them into the image classifier. So for this, we provide a video capture element. We'll give it an ID of capture, again, following basic naming here, and then on image captured, so this event is fired when the image is actually captured from the camera stream. We will tell the classifier to evaluate this image, and we give it the image parameter. So this QML, we know that the on image captured event carries an image along with it. So we're telling the classifier to evaluate that image. And then once that's complete, we can tell the capture element to go ahead and capture the next frame. And that way, basically frames in between will just get ignored until the classifier has finished doing the processing. Now the video capture is a type of video filter that uses the Qt camera API filter mechanism. So under filters here, we add capture as one of the filters. So effectively, this filter doesn't actually change the image at all. It just captures the data, converts it from YUV or whatever format is being used natively by the camera, converts it to an RGB image, wraps it into a QImage container, and fires it off. And that's why we're able to, on image capture, to the video capture element, call the classifiers evaluate using an image. So this does all that plumbing. So if we go ahead, save, and launch this application. There we go. You can see me again. Oh, I guess we forgot one important step. We of course want to see what the resulting label is. So we will add a text element inside the video output. It's not that important. Its text property, we will bind it to the classifier's label. So whenever the label changes, it'll update this text value. And then we will set the font. Let's see. Font. Font.pixel size. There we go. Make it big. And font.color. Just color. Make it white. So this should now, in the top left, give us a little text box. There we go. So, now hold up various objects. We've got a coffee mug, a banana, and soda bottle. Close enough. So that's how to quickly tie in a classifier. Next, we will show how to quickly turn this into an object detector, so I don't have to hold the objects right in the middle of the camera. We'll be able to take a few steps back and let the object detector put bounding boxes around the element. Now for this portion of the demo, we're just going to jump right into seeing the model that we'll be using, converting that model, and running it from a pre-made application we've put together. For a full demo of how the SSD detection module is put together, as well as many other demos covering everything from simple image classification to camera, video classification, object detection, pose estimation with the skeleton demo, where we look at the video frame and draw skeletons over people, as well as demonstrations of integration using GStreamer and OpenCV, as well as directly with Video for Linux. Basically all software interfaces you might be integrating with while developing an embedded Linux application. These will all be made available on our YouTube channel, along with the full documented examples as part of the DeepViewRT SDK on the Raspberry Pi release. So let's take a look at how this SSD example works now. So first we'll open up the model converter, convert the model, and then run the SSD demo application. So we have this MobileNet 2 SSD model, and in this case it's using the VOC labels list. Go ahead and convert that. And we'll now take the path to this model and provide it to our SSD sample application. Right, okay, and now we can launch the application. We should see me again. Here we go. It's person, which is correct. And now if we hold up our soda, you can see that it detects the bottle again. And this time it puts the bounding box around the object, so we know that it's detecting it in the scene. Right. So that was SSD, and again, for other various demos, such as the two you saw here, including a full walkthrough of how to put together the SSD demo, as well as a skeleton demo and other various sample integrations where we demonstrate how to work with GStreamer, with OpenCV, with Video for Linux. Sign up for the DeepViewRT on Raspberry Pi SDK, and you'll be able to download it and access all these sample projects with detailed video walkthroughs. Thank you very much.